4.2 light-years away, orbiting the nearest star to our sun, lies a world that was supposed to change everything. Proxima b, the closest exoplanet humanity will ever reach. For years, scientists celebrated its discovery as a beacon of hope, a potentially habitable world practically in our cosmic backyard. But as new instruments turned their gaze toward this neighbor, something unexpected emerged. The dark truth people whispered about, the harsh realities of life around a red dwarf. Those warnings were only the surface. What researchers have uncovered since goes far deeper, revealing not just the fate of one world, but a pattern that challenges everything we thought we understood about where life can exist in the universe. This is not a story about dashed hopes, it's a story about what comes after. When the initial excitement fades and the hard science begins. Proxima b matters in ways that transcend its own existence. It is the only potentially habitable exoplanet close enough for detailed study with current and near-future technology. Every measurement we take, every spectrum we analyze, every model we refine based on Proxima b's environment becomes the template for understanding thousands of other worlds. Red dwarfs, M-type stars like Proxima Centauri, make up roughly 70% of all stars in the Milky Way. If planets around these stars cannot support life, then the galaxy's habitable real estate shrinks dramatically. The stakes extend beyond academic curiosity. What we learn at Proxima b directly influences the design of interstellar probes, the target selection for next-generation telescopes, and our fundamental models of planetary habitability. The Breakthrough Starshot Initiative, planning to send tiny probes to Alpha Centauri at 20% light speed, has Proxima b as a primary imaging target. Billions of dollars in telescope time and mission planning hinge on understanding this world. But here's what makes this moment in astronomical history so peculiar. The more we learn about Proxima b, the more the questions multiply. The dark truth everyone discusses, the flares and radiation and tidal locking, those are settled science now. What scientists are grappling with today goes beyond those known dangers, into territory that challenges the very foundations of how we define a habitable world. Let's return to the beginning, but not the beginning you've heard before. When the European Southern Observatory announced Proxima b's discovery in August 2016, the scientific community experienced something rare, genuine surprise mixed with careful optimism. The planet had been detected using the radial velocity method, watching Proxima Centauri wobble as an orbiting planet's gravity tugged on it. The data came from the HARP spectrograph and the UVES instrument, both on the 3.6-meter telescope at La Silla Observatory in Chile. Over 16 years of observations through 2000 to 2016, astronomers accumulated enough measurements to be certain. A planet existed with a minimum mass around 1.3 times Earth's mass, orbiting every 11.2 days. The exciting part wasn't just the proximity. Proxima b orbited within what astronomers call the habitable zone, that range of distances from a star where liquid water could theoretically exist on a planet's surface. For a dim red dwarf, like Proxima Centauri, which produces only 1.7 thousandths of the sun's luminosity, the habitable zone lies extremely close. Proxima b orbits at just 0.048 astronomical units from its star, roughly 1/8 the distance between Mercury and our sun. This proximity, combined with its Earth-like mass, ignited discussions about possible atmospheres, surface water, even the remote possibility of life. But the early optimism contained a critical flaw. It relied on assumptions that were already beginning to crack under scrutiny. The habitable zone concept, elegant in theory, assumes a relatively stable star and a planet with certain atmospheric properties. It's a calculation of energy balance, where the star's radiation matches the planet's needs for maintaining liquid water. For decades, this framework guided the search for Earth-like worlds. Yet by the time Proxima b was announced, researchers studying M-dwarf systems had begun accumulating evidence that the habitable zone around red dwarfs might be more conceptual than real. The assumptions baked into those calculations, assumptions about stellar stability, about atmospheric retention, about magnetic field protection, were starting to look dangerously optimistic. Proxima Centauri is what astronomers classify as an M5.5 VE star. That final E is crucial. It indicates emission lines in the spectrum, a signature of chromospheric activity. In plain terms, it means Proxima Centauri is active, prone to outbursts and variability. Red dwarfs may be small and cool, with surface temperatures around 3,000 Kelvin compared to the Sun's 5,700, but they compensate with violence. Their convective zones extend throughout the entire stellar interior, creating powerful magnetic dynamos. These magnetic fields twist, reconnect, and unleash energy in sudden catastrophic events. However, the full extent of Proxima Centauri's volatility wasn't clear in 2016. Researchers knew about occasional flares, but the monitoring had been sporadic. Early estimates suggested Proxima b might receive flare radiation comparable to what early Earth experienced. Uncomfortable, but perhaps manageable, if the planet possessed a strong magnetic field and a thick atmosphere. This was the hopeful narrative, a narrative that recent observations have systematically dismantled. The first serious blow came in early 2018, when astronomers using multiple facilities detected a massive superflare from Proxima Centauri. On March 24, 2017, the star's brightness increased by a factor of nearly 70 in less than 2 minutes. The Everescope Array, a system of telescopes designed to monitor the entire available sky simultaneously, captured the event alongside data from the Las Cumbres Observatory, Global Telescope Network, and other instruments. The flare released energy equivalent to roughly 10 times the most powerful flare ever recorded from our Sun, the Carrington event of 1859. Yet this is where the story bends. That 2018 superflare wasn't an isolated incident. As astronomers compiled observations from various monitoring programs, a pattern emerged. Proxima Centauri produces powerful flares far more frequently than early models predicted. A 2019 study analyzing 5 years of photometric data from the MOST Space Telescope found that Proxima Centauri averaged one significant flare roughly every 3.5 days. These weren't minor fluctuations. Many reached energies between 10 to the 31st and 10 to the 32nd ergs, sufficient to deliver radiation doses to Proxima b's surface that would be devastating to any exposed organic chemistry. The implications extend beyond simple radiation exposure. Each major flare launches a coronal mass ejection, a blast of charged particles and magnetic fields that slams into any nearby planets. Earth's magnetosphere deflects most of the solar wind, but even our robust magnetic field experiences compression and storm activity during major solar events. For Proxima b, orbiting 8 times closer to its star than Mercury orbits the Sun, the particle densities and magnetic field strengths in these events are proportionally more intense. And this detail changes everything we thought about atmospheric retention. Planetary atmospheres don't just sit quietly around a world. They exist in a constant battle between gravity pulling molecules down and various escape processes lifting them away. For planets around active M-dwarfs, the primary threat isn't thermal escape, where hot atmospheric particles simply drift off into space. The threat is non-thermal escape, driven by energetic particles from the stellar wind and flare events. When high-energy protons and electrons strike atmospheric molecules, they can impart enough energy to blast them directly off the planet, even from relatively cool atmospheres. Researchers modeling this process for Proxima b have calculated sobering figures. A 2017 study by Garafo and colleagues used magnetohydrodynamic simulations to model the stellar wind from Proxima Centauri interacting with Proxima b. Their findings suggested that if Proxima b lacks a magnetic field or possesses only a weak one, the stellar wind pressure could strip away an Earth-like atmosphere in less than a few 100 million years. During superflare events, the mass loss rates spike dramatically, potentially removing the equivalent of Earth's entire atmosphere in just tens of millions of years of continuous bombardment. But here's the part scientists didn't expect. The atmospheric stripping process isn't linear or predictable. It depends critically on the planet's magnetic field strength, which in turn depends on factors we cannot directly observe: the planet's rotation rate, its internal heat flow, the composition of its core. Tidal locking, which Proxima b has almost certainly experienced given its close orbit, complicates everything. A tidally locked planet keeps one face toward its star perpetually, just as the moon keeps one face toward Earth. This synchronous rotation dramatically slows the planet's spin relative to a non-tidally locked world. Slow rotation means a weaker magnetic dynamo. Earth's magnetic field arises from the churning of liquid iron in its outer core, a process driven partly by the planet's relatively rapid rotation. If Proxima b rotates once every 11 days, the same as its orbital period, its dynamo mechanism would be far less efficient. Some models suggest tidally locked planets around M-dwarfs might possess magnetic fields only 10% as strong as Earth's, or weaker still. Without a robust magnetosphere, the stellar wind and flare particles have direct access to the upper atmosphere. The scenario becomes even more complex when considering the early history of M-dwarf systems. Young red dwarfs are extraordinarily active, producing flares and stellar winds, orders of magnitude more intense than they do in their mature years. Proxima Centauri, estimated to be around 4.8 billion years old, has calmed considerably since its youth. But during its first few 100 million years, the bombardment would have been relentless. If Proxima b formed with an atmosphere, whether from outgassing during planetary formation or from later delivery by comets and asteroids, that early atmosphere faced immediate and overwhelming assault. However the deeper researchers looked, the stranger it became. Atmospheric modeling isn't just about removal. It's also about chemistry, about what happens to molecules when they're bathed in intense ultraviolet and X-ray radiation. Red dwarfs emit proportionally more of their energy in these high-energy wavelengths than sun-like stars do. For Proxima Centauri, the X-ray luminosity is roughly 400 times greater than the Sun's, relative to total luminosity. When high-energy photons strike atmospheric molecules like water vapor, carbon dioxide, or molecular nitrogen, they break chemical bonds, creating radicals and ions that participate in complex photochemical reactions. In Earth's atmosphere, similar processes occur, but are balanced by the chemistry of life and geological recycling. Plants produce oxygen, which forms ozone, which absorbs ultraviolet radiation and protects the surface. Volcanic activity releases gases that replenish what's lost to space and chemical reactions. For Proxima b, without life and without observed geological activity, the photochemical destruction could create a runaway effect. Water molecules split into hydrogen and oxygen. The light hydrogen escapes to space quickly. The oxygen, instead of accumulating as a potential biosignature, reacts with surface minerals, forming oxides. The planet becomes a desiccated, oxidized husk. This is what researchers now call the photochemical trap for M-dwarf planets. The very radiation that might drive interesting chemistry also prevents the accumulation of potentially life-supporting compounds. A 2020 study by Chen and colleagues modeled the atmospheric photochemistry of planets in the habitable zones of M-dwarfs and found that many plausible atmospheric compositions would be unstable on timescales of mere tens of millions of years. The atmosphere doesn't just thin out, it transforms chemically into something unrecognizable, hostile, depleted of volatiles. And this is where the data refuses to behave according to comfortable predictions. Despite all these challenges, some models suggest Proxima b might still possess an atmosphere under specific conditions. If the planet formed with a massive volatile inventory, perhaps hundreds of times Earth's atmospheric mass, enough might remain after billions of years of erosion. Alternatively, if geological processes continue to outgas new atmosphere at a sufficient rate, a steady state could exist where loss and replenishment balance. Some researchers propose that a subsurface ocean, protected beneath kilometers of ice, could serve as a reservoir, feeding atmospheric water vapor through cryovolcanism or sublimation processes. The truth is, we don't know. And that uncertainty contains both frustration and possibility. Direct detection of Proxima b's atmosphere has so far eluded astronomers. The planet doesn't transit its star from our viewing angle, meaning we can't use transit spectroscopy, the primary method for analyzing exoplanet atmospheres. During a transit, starlight filters through the planet's atmosphere, and molecules absorb specific wavelengths, creating a signature spectrum. Without transits, astronomers must rely on other techniques. Measuring the planet's thermal emission, searching for reflected light, or attempting direct imaging at infrared wavelengths, where the contrast between star and planet is more favorable. The James Webb Space Telescope, operational since mid-2022, offers new capabilities but also new challenges. JWST's infrared sensitivity could theoretically detect thermal emission from Proxima b, but the planet's proximity to its extremely bright star makes separation difficult. Even with coronagraphic techniques to block starlight, the observation requires exceptional precision and long integration times. As of late 2024, no confirmed atmospheric detection has been reported, though observing proposals continue to be submitted for future cycles. Yet this is where the story expands beyond a single planet's fate. The challenges facing Proxima b are not unique. They are systematic, shared by potentially thousands of exoplanets discovered around M-dwarf stars. The Transiting Exoplanet Survey Satellite, TESS, has found dozens of small planets orbiting red dwarfs in their habitable zones. Each one faces similar questions about stellar activity, atmospheric retention, and photochemical stability. What makes Proxima b extraordinary is not that it's special, but that it's close enough for us to study in detail. The answers we eventually obtain will echo across exoplanet science, reshaping our understanding of habitability everywhere. Consider the broader context. The 7 planets of the TRAPPIST-1 system orbit an even cooler M-dwarf, with at least 3 worlds in the habitable zone. Early excitement about these planets has tempered as atmospheric studies reveal complications. JWST observations of TRAPPIST-1b and TRAPPIST-1c suggest little to no atmosphere, consistent with models of atmospheric erosion. If this pattern holds across M-dwarf systems, then the galaxy's most numerous stars might host rocky planets in abundance, but habitable worlds in scarcity. The irony is profound. M-dwarfs live for trillions of years, far longer than sun-like stars. They offer vast stretches of time for life to develop, evolve, and persist. But if their planets cannot maintain habitable conditions for even a fraction of that duration, the longevity becomes irrelevant. Time without opportunity equals nothing. This is the existential puzzle at the heart of red dwarf habitability studies. But there's another layer to Proxima b's story that recent research has begun to illuminate, a dimension that extends beyond the planet itself into the dynamics of the Alpha Centauri system. Proxima Centauri is not alone. It orbits in a wide triple system with Alpha Centauri A and B, 2 sun-like stars that form a closer binary pair. The distance between Proxima and the AB pair is roughly 13,000 astronomical units, about 1/5 of a light year. At such distances, the gravitational influence is weak, but not negligible over billions of years. Orbital mechanics become a slow dance of perturbations, where slight tugs accumulate into significant changes over deep time. In 2019, astronomers announced a second planet candidate in the Proxima system, Proxima c. This world, if confirmed, is more massive than Proxima b, with a minimum mass around 6 Earth masses, and orbits much farther out at roughly 1.5 astronomical units, with a period of about 5.2 years. Proxima c would lie well beyond the habitable zone, receiving less than 10% of Earth's solar energy, making it a frozen super-Earth or mini-Neptune. Its existence, still debated in some circles due to the subtlety of the detection signal, raises fascinating questions about planet formation and migration in this system. How did Proxima Centauri, a relatively low-mass star, form planets massive enough to create detectable radial velocity signals? Planet formation theory suggests that protoplanetary disks around M-dwarfs should contain less material than disks around sun-like stars. Yet the presence of Proxima b, and possibly Proxima c, implies a relatively robust disk in the system's early history. Some models propose that gravitational interactions with Alpha Centauri A and B during the system's formation could have influenced the disk's mass and structure, perhaps even triggering enhanced accretion or altering migration patterns. The presence of a second planet also introduces dynamical considerations for Proxima b's habitability. Multi-planet systems exhibit gravitational interactions that evolve over time. Orbital resonances can stabilize or destabilize planetary configurations. Eccentric orbits can pump tidal heating into planets, potentially maintaining geological activity. For Proxima b, if Proxima c exists and the 2 planets have undergone any significant orbital evolution, the history of tidal heating, orbital eccentricity, and rotational state could be far more complex than simple models assume. And this detail opens unexpected possibilities. Tidal heating, the same process that drives volcanic activity on Jupiter's moon Io and keeps Europa's subsurface ocean liquid, could provide an internal heat source for Proxima b, independent of stellar radiation. If the planet possesses even a modest orbital eccentricity, perhaps maintained by gravitational interactions with Proxima c, tidal flexing would generate heat in the interior. This heat could drive volcanism, plate tectonics, and atmospheric outgassing, potentially counterbalancing atmospheric loss and creating a more dynamic, geologically active world than static models predict. The challenge lies in the unknowns. We cannot directly measure Proxima b's orbital eccentricity with current data precision. The radial velocity method provides minimum masses and orbital periods, but struggles with parameters like eccentricity for planets, with short periods and small signal amplitudes. Future observations with instruments like the extremely large telescopes Ristretz and Metis instruments might refine these measurements. But for now, uncertainty dominates. Yet even within uncertainty, patterns emerge. Researchers studying the broader population of M-dwarf planets have noticed something curious. Short-period planets, those orbiting very close to their stars like Proxima b, often show hints of maintained geological activity based on statistical analyses of their bulk compositions and density distributions. The mechanism remains unclear, whether tidal heating, residual primordial heat, or other energy sources. But the implication is that some rocky planets around red dwarfs might remain internally active for billions of years. This matters because internal activity drives planetary magnetic fields. If Proxima b has sustained geological activity, it might generate a magnetic field after all, despite tidal locking. Unusual core compositions, perhaps enriched in radioactive elements or possessing a layered structure, could maintain a dynamo even with slow rotation. Magnetic field generation is not fully understood, even for Earth. The diversity of planetary interiors could produce magnetic behaviors we haven't yet imagined. However, there's a deeper current running through these discussions, something that has only recently surfaced in the technical literature. The early history of planetary systems around M-dwarfs might be far more violent than around sun-like stars. Red dwarfs take hundreds of millions of years to settle onto the main sequence, contracting slowly and remaining highly active throughout this pre-main sequence phase. During this time, they produce intense stellar winds, frequent superflares, and extreme ultraviolet and X-ray emission. Any planets forming or migrating inward during this period face a radiation environment orders of magnitude harsher than anything in our solar system's history. A 2021 study by Howard and colleagues modeled the pre-main sequence evolution of M-dwarfs and calculated the cumulative radiation dose received by close-in planets. Their findings suggest that planets like Proxima b could have experienced surface radiation equivalent to billions of years of current stellar activity, compressed into the first 100 million years. Under such bombardment, not only would atmospheres be stripped, but surface rocks would be altered, volatiles baked away, and the entire near-surface environment sterilized down to significant depths. This paints a grim picture, but it also raises a provocative question. If Proxima b formed farther from its star and migrated inward later, after Proxima Centauri had settled into a calmer state, it might have avoided the worst of the early bombardment. Planet migration is common in exoplanetary systems, driven by interactions with the protoplanetary disk or gravitational scattering between planets. If Proxima b originated beyond the snow line and spiraled inward after the disk dispersed, it could have delivered a substantial volatile inventory to its current position relatively intact. The problem is distinguishing between formation scenarios. Did Proxima b form in situ, where we find it today? Did it migrate inward from a more distant orbit? Was it captured from another system during a close stellar encounter in the early history of Alpha Centauri? Each scenario produces different predictions about the planet's composition, internal structure, and volatile inventory. But testing these predictions requires data we don't yet possess. And this is where the conversation shifts from what we know to what we're beginning to suspect. The Alpha Centauri system is gravitationally bound, but loosely so. The orbital dynamics allow for complex interactions over billion-year timescales. Some researchers have proposed that Proxima Centauri might have captured planets from the Alpha Centauri AB disk, or vice versa, during periods when the stellar orbits brought them closer together. Planet exchange between stars in wide binary or triple systems is theoretically possible, though observationally unconfirmed. If Proxima b originated around Alpha Centauri A or B and was later transferred to Proxima, its composition and formation history would reflect conditions around a Sun-like star, not an M-dwarf. This scenario, admittedly speculative, fits some puzzling features of the Proxima system. The presence of relatively massive planets around such a low-mass star remains somewhat surprising. The potential existence of Proxima c far from the star resembles the architecture of planets around solar-mass stars, more than typical M-dwarf systems. If planet capture occurred, it would explain these anomalies elegantly. But speculation requires evidence, and evidence in exoplanetary science is hard-won. Every measurement pushes the boundaries of current technology. Every model relies on assumptions that may or may not reflect reality. The honest truth is that Proxima b remains in many ways a mystery. We know it exists. We know its approximate mass and orbital period. Everything else, from its radius to its composition to its atmospheric state, remains uncertain or unknown. Yet uncertainty is not the end of science. It's the beginning. Each unknown parameter represents a question that future observations might answer. Each competing model generates predictions that can, in principle, be tested. The work continues, methodically, accumulating data point by data point. In recent years, the focus has broadened from simple questions of habitability to more nuanced investigations of planetary physics. Researchers are now asking not just, could Proxima b be habitable? But, what can Proxima b teach us about planetary evolution, atmospheric dynamics, and the limits of rocky planet diversity? The shift reflects a maturation in exoplanet science, moving beyond the binary of habitable versus uninhabitable toward a richer understanding of planetary processes. One emerging area of study concerns the potential for alternative biochemistries. If Proxima b possesses a thick atmosphere rich in hydrogen, very different from Earth's nitrogen-oxygen mixture, might life adapt to those conditions? Hydrogen atmospheres are poor insulators, but could support aerial ecosystems in upper atmospheric layers, where temperatures and pressures reach habitable ranges. This is highly speculative, bordering on astrobiology's fringes, but it illustrates how thinking about Proxima b has evolved. The planet need not be an Earth twin to be interesting or even biologically significant. Another line of investigation involves the search for technosignatures. If intelligent life arose anywhere in the Alpha Centauri system, deliberate signals or technological artifacts might be detectable. The Breakthrough Listen initiative has conducted extensive radio and optical searches targeting Proxima Centauri, so far without positive results. The absence of detectable signals doesn't rule out the presence of life, technological or otherwise, but it constrains the possibilities. Any civilization transmitting powerful radio signals from Proxima b would be easily detected by current instruments. The silence is informative, if disappointing. The James Webb Space Telescope's extended mission will likely include more attempts to characterize Proxima b's environment. Mid-infrared observations could detect thermal emission if the planet has a hot day side and the observation geometry is favorable. High-resolution spectroscopy might reveal molecular features in reflected light, though this pushes the telescope's capabilities. Each observing proposal competes with dozens of other high-priority targets, from distant galaxies to nearby exoplanets, making telescope time a precious and fiercely contested resource. Ground-based, extremely large telescopes currently under construction, the European Extremely Large Telescope in Chile, and the 30-meter telescope planned for Hawaii or the Canary Islands, will bring new capabilities online in the coming years. These instruments will possess the light-gathering power and angular resolution to directly image planets around nearby stars, including potentially Proxima b. Direct imaging would allow continuous monitoring, tracking changes in brightness and color as the planet rotates, revealing weather patterns, cloud cover, and surface features. It would transform Proxima b from an indirect detection, a wobble in a star's spectrum, into a world we can actually see. Yet even as technological capabilities advance, theoretical understanding lags in some areas. The physics of atmospheres on tidally locked planets remains incompletely understood. Early models predicted extreme temperature contrasts between day and night hemispheres, with all volatiles freezing out on the dark side. More sophisticated simulations incorporating atmospheric circulation show that winds can redistribute heat, moderating the temperature gradient. However, these models depend on assumptions about atmospheric composition, pressure, and rotation rate, all unknown for Proxima b. The concept of terminator habitability has gained traction in recent discussions. On a tidally locked world, the terminator, the twilight zone between eternal day and eternal night, might offer the most clement conditions. Here, the star hangs perpetually on the horizon, providing constant low-angle illumination without the intensity of the substellar point directly beneath the star. Temperatures could remain moderate, and if the atmosphere circulates effectively, liquid water might exist in a narrow habitable band circling the planet. Life, if it exists, might be confined to this twilight region, adapted to the strange perpetual sunset or sunrise conditions. This scenario, while intriguing, requires a substantial atmosphere to function. Without atmospheric heat redistribution, the terminator zone would experience wild temperature fluctuations as local conditions shift. And we return again to the central question: does Proxima b have an atmosphere? And if so, what is its composition and pressure? Until we answer this, much of the theoretical edifice remains untested speculation. And yet, despite everything already uncovered, Researchers now suspect that the most important chapter of this story has not even been opened. The challenges facing Proxima b, the stellar activity, the atmospheric erosion, the tidal locking, these are symptoms of a larger structure. What Proxima Centauri represents, what M-dwarf planetary systems reveal, extends beyond individual worlds into questions about stellar evolution, galactic habitability, and the fundamental relationship between stars and the planets they host. The data emerging from observations of Proxima b and other red dwarf systems suggests patterns that current models do not fully capture. Anomalies in stellar activity cycles, unexpected correlations between planet presence and stellar magnetic behavior, hints that the early bombardment phase might be more varied than simple age-based models predict. What Proxima b shows us in its proximity and its mysteries may only be the first shadow of a far larger pattern. The dark truth about our nearest neighbor was never just about one planet's hostile environment. It was always about what that environment reveals, about the architecture of planetary systems around the galaxy's most common stars, about the intersection of stellar physics and planetary evolution, about the boundaries of habitability and the resilience or fragility of atmospheres under extreme conditions. We have learned much, but the deeper questions, the questions about how common Earth-like conditions truly are, about whether red dwarfs represent havens or dead ends for life, about what billions of years of evolution under a crimson sun might produce, those questions remain open. And answering them requires moving beyond Proxima b itself, into the broader context of the Alpha Centauri system, into the comparative study of M-dwarf planets across the galaxy, into the synthesis of observation and theory that defines modern astrophysics. Proxima b, the dark truth about our neighbor, was only the beginning. Part 2. The pattern emerged slowly, hidden in decades of data that astronomers initially overlooked. When researchers began compiling comprehensive activity records for red dwarf stars, comparing them against planetary detection statistics, something unexpected appeared in the correlations. Stars with confirmed planets showed different magnetic behavior than those without. Not dramatically different, but measurably so. The distinction was subtle enough that early surveys missed it entirely, but as sample sizes grew and analysis techniques improved, the signal strengthened. By 2022, multiple independent studies confirmed the finding. Planet-hosting M-dwarfs exhibited statistically distinct patterns in their flare frequency distributions, their X-ray emission levels, and their rotation activity relationships. This discovery opened questions that reach far beyond Proxima b alone. If planets influence their host stars' magnetic activity, then the relationship between star and planet is more dynamic, more interactive than classical models assumed. And if that relationship varies depending on planetary properties, mass, orbital distance, magnetic field strength, then each planetary system becomes not just a star with orbiting worlds, but a coupled system, where components influence each other across millions of kilometers of space. The implications cascade outward. Stellar activity shapes planetary atmospheres through radiation and particle bombardment. But if planets also shape stellar activity, even modestly, then the evolution of planetary habitability becomes a feedback loop rather than a one-way street. Understanding this loop requires examining not just Proxima Centauri and its planets, but the broader population of M-dwarf systems, searching for patterns that reveal the underlying physics. Let's examine what researchers have learned from comparative studies of red dwarf planetary systems and what those lessons mean for interpreting Proxima b's environment. The TRAPPIST-1 system, discovered in 2017, provided the first opportunity to study multiple terrestrial planets around a single M-dwarf. 7 planets, all roughly Earth-sized, orbit an ultra-cool M8 dwarf star 40 light-years away. 3 of these worlds, TRAPPIST-1e, F, and G, reside in the traditional habitable zone. The system's geometry allows all 7 planets to transit their star from Earth's perspective, making it ideal for atmospheric characterization studies. Initial excitement centered on the possibility of finding biosignatures in multiple atmospheres, potentially establishing a habitable zone populated with living worlds. Reality proved more complex. The James Webb Space Telescope began observing TRAPPIST-1 planets in 2022, starting with the innermost worlds. TRAPPIST-1b, scorched by intense stellar radiation with an equilibrium temperature around 400 Kelvin, showed no evidence of an atmosphere in JWST's mid-infrared observations. The lack of atmospheric features suggested either an airless rock or an atmosphere so tenuous that it produces no detectable spectral signature. TRAPPIST-1c, slightly farther out but still inside the habitable zone, yielded similar results. No signs of carbon dioxide, water vapor, methane, or other expected atmospheric constituents. The pattern suggested systematic atmospheric loss, consistent with models of erosion by stellar wind and flare activity. TRAPPIST-1, despite being cooler and dimmer than Proxima Centauri, produces violent flares and strong magnetic activity. The star's youth, estimated at around 8 billion years, means it has spent more time in an active state than it will spend in its eventual quiescent phase billions of years hence. Its planets have endured eons of bombardment. However, the deeper implications extend beyond atmospheric loss. The TRAPPIST-1 system's architecture reveals clues about planet formation and migration around M-dwarfs. All 7 planets orbit within a distance comparable to Mercury's orbit around the Sun. They exist in a tightly packed configuration, with orbital periods ranging from 1.5 days for planet B to nearly 19 days for planet H. Such architectures require specific formation scenarios, likely involving inward migration through a gas-rich protoplanetary disk, followed by dynamical interactions that establish the current orbital resonances. The resonances themselves are remarkable. Multiple planets in the TRAPPIST-1 system are locked in mean motion resonances, where their orbital periods form simple integer ratios. These resonances stabilize the system, preventing close encounters that would lead to collisions or ejections. But they also facilitate gravitational interactions that drive tidal heating. Models suggest that some TRAPPIST-1 planets, particularly those in the middle of the system, might experience significant tidal heating comparable to or exceeding the stellar heating they receive. This internal heat source could maintain geological activity, drive volcanism, and potentially support subsurface oceans even on planets that appear inhospitable from external radiation alone. And this is where the story connects back to Proxima b. If tidal heating plays a significant role in TRAPPIST-1, might it also matter for Proxima's planets? The presence of Proxima c, if confirmed, establishes a multi-planet system capable of gravitational interactions. The current orbital configuration might not tell the full story. Migration history, past resonances, and dynamical evolution could have imprinted tidal heating episodes on Proxima B's interior that continue to influence its geological state today. But there's another dimension to consider, one that emerged from studies of stellar magnetic cycles and their relationship to planetary systems. Our Sun exhibits an 11-year magnetic activity cycle where sunspot numbers, flare frequencies, and solar wind properties oscillate between minimum and maximum states. This cycle arises from the Sun's internal magnetic dynamo, the complex interactions between rotation, convection, and magnetic field generation in the solar interior. Other Sun-like stars show similar cycles, though with varying periods and amplitudes. For decades, astronomers assumed M-dwarfs would follow comparable patterns, though the details might differ due to their fully convective interiors. Recent long-term monitoring has revealed surprises. Some M-dwarfs do exhibit cyclic activity variations, but others show erratic, seemingly random fluctuations with no clear periodicity. A 2020 study analyzing 40 years of chromospheric activity. Indicators for nearby M-dwarfs found that roughly half displayed identifiable cycles, while the remainder showed either irregular variability or no detectable pattern at all. The distinction correlated weakly with stellar rotation rate and age, but not strongly enough to constitute a predictive relationship. Proxima Centauri falls into the irregular category. Decades of photometric and spectroscopic monitoring show variable activity levels, but no clear cycle. Some years exhibit frequent powerful flares. Other periods remain relatively quiescent. The variability appears chaotic, lacking the predictable rhythm of solar-type cycles. This irregularity complicates attempts to model long-term effects on Proxima b, a planet experiencing randomly timed superflare bombardment faces different evolutionary pressures than one subjected to predictable activity cycles, where atmospheric recovery might occur during quiet phases. Yet this irregularity might itself be informative. Some theoretical models propose that planet-star magnetic interactions could disrupt or modify stellar activity cycles. If a planet possesses a strong magnetic field, the interaction between planetary and stellar magnetic fields during close approaches might trigger reconnection events, launching flares or altering the star's global magnetic topology. Evidence for such interactions remains tentative, observed in a handful of hot Jupiter systems where planets orbit extremely close to their stars. But the physics suggests the phenomenon could occur across various system architectures. For Proxima b, the question becomes whether its potential magnetic field influences Proxima Centauri's activity. The planet's 11-day orbit brings it within 5 million kilometers of the star's surface, close enough that magnetic field interactions are plausible if both bodies possess sufficiently strong fields. Detecting such interactions requires precise timing of flare events correlated with orbital phase, searching for patterns where flares preferentially occur when the planet occupies specific positions. Analysis of existing data has not yielded clear detections, but the statistical power remains limited by incomplete observational coverage. However, there's a deeper question lurking beneath these technical details. If star-planet magnetic interactions occur, they represent energy transfer mechanisms that could, over billions of years, alter both the stellar and planetary magnetic dynamos. Energy dissipated through magnetic reconnection comes from somewhere, either the star's rotational energy or the planet's orbital energy. Over time, such energy losses could modify rotation rates, orbital distances, or magnetic field strengths. the effects would be small, easily lost in the noise of other evolutionary processes. But on billion-year timescales, small effects accumulate, and this detail opens unexpected territory. The current state of any planetary system represents a snapshot in a continuous evolution spanning the system's entire lifetime. Understanding Proxima b requires reconstructing its history, tracing how it arrived at its current configuration from initial formation conditions billions of years ago. This reconstruction depends on models of orbital migration, tidal evolution, atmospheric escape, magnetic field generation, and geological activity, all interacting in ways that current theory only partially captures. Let's consider the tidal evolution more carefully, because it constrains much about Proxima b's current state. When a planet orbits close to its star, tidal forces raise bulges in both the planet and the star. These bulges experience drag from internal friction as the bodies rotate, dissipating energy and exerting torques that alter rotation rates and orbital distances. For Proxima b, the initial spin rate after formation, perhaps 10 to 20 hours for a rapid primordial rotation, would have gradually slowed under tidal torques until it reached synchronous rotation matching the orbital period. This process, called tidal locking, occurs relatively quickly for close-in planets. Estimates for Proxima b suggest tidal locking occurred within the first 100 million years of its existence, possibly much faster. Once tidally locked, the planet's rotation rate remains fixed at the orbital period, approximately 11 days. But tidal evolution doesn't stop. If the orbit possesses any eccentricity, the planet's distance from the star varies during each orbit, creating time-varying tidal forces that continue to dissipate energy. This energy dissipation generates heat in the planet's interior, drives tidal circularization that gradually reduces orbital eccentricity, and slowly migrates the orbit outward as angular momentum transfers from the planet's rotation to its orbital motion. The timescales for these processes depend critically on the planet's internal structure, particularly the rigidity and viscosity of its interior layers. A planet with a large molten core and partially molten mantle dissipates tidal energy more efficiently than a fully solid body. For Earth-mass planets, current models suggest that significant tidal heating requires orbital eccentricities of at least a few percent and favorable internal properties. Whether Proxima b meets these conditions remains unknown. But here's what makes this particularly interesting for habitability. Tidal heating is independent of stellar radiation. A planet could be located far from its star, receiving minimal sunlight, yet remain warm internally from tidal dissipation. Europa and Enceladus in our solar system demonstrate this principle, maintaining subsurface oceans through tidal heating generated by gravitational interactions with Jupiter and Saturn respectively. For Proxima b, even modest tidal heating could power geological activity, drive plate tectonics, and maintain a magnetic dynamo, all of which enhance habitability prospects. The challenge lies in determining whether Proxima b actually experiences significant tidal heating. The orbital eccentricity remains poorly constrained. Radial velocity measurements provide upper limits, suggesting eccentricity less than about 0.1, but the true value could be much smaller, or even effectively zero. Future observations with more precise spectrographs or direct imaging that reveals orbital motion might refine this parameter. Until then, models must consider a range of possibilities. Yet even as we grapple with unknowns about Proxima b specifically, The broader context of M-dwarf planets provides valuable constraints through statistical arguments. Surveys have now detected hundreds of planets around M-dwarf stars. The Kepler Space Telescope, during its primary and extended missions, identified numerous small planets orbiting red dwarfs. TESS continues this census, finding new worlds monthly. Statistical analyses of these populations reveal trends in planet occurrence rates, radius distributions, and orbital architectures. One consistent finding is that small planets, those with radii between Earth's and Neptune's, are extremely common around M-dwarfs. Occurrence rates suggest that nearly every M-dwarf hosts at least one small planet, and many host multiple worlds. This abundance implies robust planet formation processes around low-mass stars. The protoplanetary disks surrounding young M-dwarfs contain sufficient material to build planetary systems despite the limited mass of the host star. The prevalence of close-in planets, those with orbital periods less than 50 days, suggests either preferential formation at small orbital distances or efficient inward migration. Distinguishing between these scenarios requires understanding disk properties and migration physics in detail. However, the abundance of planets does not directly translate to abundance of habitable worlds. Most detected M-dwarf planets orbit too close to their stars, receiving stellar radiation that renders them inhospitable by conventional standards. The habitable zone planets, while present in the population, represent a smaller subset. And as we've seen with TRAPPIST-1 and Proxima b, occupying the habitable zone guarantees neither the presence of an atmosphere nor the existence of liquid water. The statistical picture suggests a galaxy filled with rocky planets around red dwarfs, but with uncertain prospects for life. This conclusion, sobering as it might be, remains preliminary. We have characterized atmospheres for only a handful of M-dwarf planets. The sample remains heavily biased toward easy targets, the hottest planets with the largest atmospheric signals. Cooler, potentially habitable worlds require longer observing times and more sensitive instruments. The absence of detected atmospheres on some planets does not prove that all similar planets lack atmospheres, only that the specific observed cases do. And this is where the data refuses to settle into comfortable conclusions. For every negative result, there are reasons to maintain some optimism. A 2023 study of the planet LHS 1140b, a super-Earth orbiting in the habitable zone of a nearby M-dwarf, reported intriguing hints of an atmosphere based on JWST observations. The data suggested possible water vapor absorption features, though not at high enough confidence to constitute a definitive detection. If confirmed with follow-up observations, LHS 1140b would represent the first habitable zone M-dwarf planet with an atmosphere, demonstrating that atmospheric retention is possible under the right conditions. The planet's larger mass, about 6 Earth masses, might provide stronger gravity to hold on to volatiles. Its host star, while still active, produces fewer extreme flares than Proxima Centauri or TRAPPIST-1. This potential detection, even if ultimately proven spurious, illustrates an important point. The diversity among M-dwarf systems means that conclusions drawn from a few examples might not generalize. Proxima b's harsh environment might represent one end of a spectrum rather than the typical case. Cooler, less active M-dwarfs might offer more clement conditions. Planets with specific formation histories, those that accreted large volatile inventories or formed in situ rather than migrating, might fare better. The parameter space is vast, and our exploration has barely begun. But there's another angle to this story, one that recent theoretical work has begun to explore. The concept of habitability itself might be too narrowly defined, too focused on Earth analog conditions. Traditional habitability criteria emphasize liquid water on a planet's surface, moderate temperatures, and atmospheric conditions compatible with carbon-based biochemistry as we know it. These criteria make sense given Earth is our only example of a living world, but they might miss other possibilities. Life, at its most fundamental level, requires energy gradients to exploit, complex chemistry to build structures, and solvents to facilitate reactions. Water serves these functions admirably, but other substances might work in different temperature and pressure regimes. For Proxima b, if the planet lacks surface liquid water due to stellar activity or tidal locking issues, might alternative habitats exist? Subsurface environments, protected from radiation by kilometers of rock and ice, could maintain liquid water in contact with heated rock, creating conditions similar to Earth's deep ocean hydrothermal vents. Life on Earth thrives in such environments, independent of sunlight, drawing energy from chemical reactions between seawater and minerals. A subsurface biosphere on Proxima b would be invisible to remote sensing, undetectable by any telescope currently conceived, yet potentially thriving nonetheless. Alternatively, if Proxima b possesses a thick, hydrogen-rich atmosphere, the upper atmospheric layers might offer habitable zones where temperature and pressure allow chemical complexity. Aerial ecosystems, organisms floating in atmospheric currents and deriving energy from photochemistry or electrical discharges, represent speculative but not impossible biology. Earth's atmosphere hosts microbial life at high altitudes, and Jupiter's clouds might harbor chemical processes bordering on the prebiotic. Extending these concepts to exoplanets expands the range of potentially habitable conditions. These scenarios, admittedly speculative, serve a purpose. They prevent premature closure on questions that remain open. The absence of an Earth-like environment does not equal the absence of habitability in all forms. As astrobiology matures, the field increasingly recognizes that life might adapt to conditions we find extreme, or even assume to be completely sterile. The limits of life remain poorly understood. Every few years, terrestrial discoveries of organisms thriving in previously thought uninhabitable environments, deep in Antarctic ice, in highly acidic or alkaline waters, in radiation-saturated locations near nuclear reactors, expand our understanding of biological possibility. However, speculation must be balanced with rigor. The burden of proof for exotic life forms is high, and rightly so. Extraordinary claims require extraordinary evidence. Until we develop methods to test these hypotheses, either through direct exploration or refined remote sensing, they remain possibilities rather than established facts. Let's return to what we can observe and measure. The physics and chemistry that constrain Proxima b's environment, regardless of biological considerations. One critical question concerns the planet's bulk composition. Is Proxima b a predominantly rocky world, similar to Earth or Venus, with an iron core and silicate mantle? Or does it contain substantial water ice, making it a water world, with a global ocean potentially hundreds of kilometers deep, overlying a rocky core? The mass and radius determine bulk density, which constrains composition, but we don't know Proxima b's radius. The planet doesn't transit, preventing direct radius measurement. Estimates based on mass-radius relationships for rocky planets suggest a radius between 1 and 1.3 Earth radii, but uncertainty remains large. The compositional question matters because it affects everything from atmospheric evolution to geological activity. A water-rich world might maintain a thick steam atmosphere if temperatures are high enough, or a global ice shell if temperatures drop below freezing. Such planets might undergo runaway greenhouse effects more easily than primarily rocky worlds, as water vapor is a powerful greenhouse gas. Conversely, if tidal heating occurs, a water-rich mantle could dissipate energy more efficiently through convection, maintaining geological activity longer than a drier planet. Theoretical models of planet formation around M-dwarfs provide some guidance. Planets forming beyond the snowline, the distance from the star where water ice condenses in the protoplanetary disk, should incorporate substantial ice and volatiles. For M-dwarfs, the snowline lies very close to the star during disk evolution due to the low stellar luminosity. Planets forming at Proxima B's current location would have formed inside the snowline, accreting mainly rocky and metallic materials with limited volatiles. However, if Proxima B migrated inward from a more distant formation location, it could have formed as a water-rich world and subsequently delivered that water inventory to its current orbit. Migration scenarios are common in exoplanet systems. The prevalence of hot Jupiters, gas giant planets orbiting extremely close to their stars, demonstrates that significant inward migration occurs. Rocky planets can migrate similarly, driven by gravitational interactions with the protoplanetary disk or with other planets. Whether Proxima B migrated remains speculative, but the possibility influences our expectations for its composition and habitability. And this brings us to one of the most intriguing recent developments in understanding the Alpha Centauri system, a discovery that reframes how we think about the planets around Proxima Centauri. In 2021, astronomers using the Very Large Telescope in Chile reported the possible detection of a third planet candidate in the Proxima system, designated Proxima D. This candidate, if real, would be extremely small, with a minimum mass around 1/4 of Earth's mass, making it one of the lowest mass exoplanets ever detected by radial velocity. It orbits very close to the star, with a period of just 5 days and an orbital distance of only 0.029 astronomical units. At such proximity, the planet receives nearly 10 times more radiation than Earth does from the Sun, rendering it far too hot for liquid water. Its existence, tentative and requiring confirmation, nonetheless suggests that the Proxima system might host more planets than currently confirmed. The significance extends beyond simple planet counting. If Proxima hosts 3 or more planets, the system's dynamical history becomes richer and more complex. Multiple planets interact gravitationally, exchanging energy and angular momentum in ways that shape orbital architectures over time. Resonances can form, locking planets into stable configurations. Chaotic interactions can eject planets or drive collisions. The current orbital arrangement represents the outcome of billions of years of such interactions. For Proxima b, the presence of additional planets, both interior and exterior to its orbit, means its dynamical evolution was not isolated. The planet's current orbital eccentricity, its rotational state, and its tidal heating history all depend on past gravitational interactions with sibling worlds. If the system underwent a phase of dynamical instability, common in multi-planet systems, Proxima b might have experienced close encounters that excited its orbital eccentricity or altered its spin state before tidal forces restored synchronous rotation. These dynamical considerations connect to observational puzzles that have emerged from detailed studies of Proxima Centauri's variability. The star's rotation period, measured from star spot modulations and chromospheric activity indicators, is approximately 83 days. This is unusually slow for an M-dwarf of Proxima's age. Most M-dwarfs in the solar neighborhood with similar ages rotate considerably faster, with periods between 20 and 50 days. Slow rotation typically results from magnetic braking, where the star's magnetic field interacts with its stellar wind to carry away angular momentum over time. But Proxima's rotation rate appears slower than models predict based on its age and mass. One speculative explanation involves planet-star interactions. If planets can transfer angular momentum to or from the star through magnetic or tidal coupling, they might influence stellar rotation rates over long timescales. Evidence for such effects remains minimal, but the physics is plausible under certain conditions. If Proxima b or other planets in the system have significantly affected the star's rotation, it would represent a profound example of planetary influence on stellar evolution. Alternatively, Proxima's slow rotation might simply reflect initial conditions or idiosyncratic magnetic braking history. Stars exhibit substantial diversity even within narrow parameter ranges of mass and age. Not every unusual property requires exotic explanations. However, the deeper researchers examined Proxima Centauri's properties, the more anomalies accumulated. The star's metallicity, the abundance of elements heavier than hydrogen and helium, is slightly higher than the Sun's despite being older. This is not necessarily contradictory, as stars form from interstellar material with varying compositions depending on location and time, but it does suggest that Proxima's birth environment differed from the Sun's. Higher metallicity generally favors planet formation by providing more solid material in the protoplanetary disk. The presence of multiple planets around Proxima, despite its low mass, aligns with this expectation. The metallicity also affects stellar structure and evolution. Higher metal content increases opacity in the stellar interior, altering how energy is transported by radiation versus convection. These changes influence the magnetic dynamo, potentially affecting activity levels and flare frequencies. Whether Proxima's metallicity contributes to its high activity level remains an open research question. And this is where the conversation shifts from individual stellar and planetary properties to the broader context of the Alpha Centauri triple system and its formation history. Alpha Centauri A and B, the two sun-like stars in the system, orbit each other with a period of roughly 80 years. Their orbit is eccentric, bringing them as close as 11 astronomical units and separating them to as far as 36 astronomical units. Proxima Centauri, orbiting the pair at a distance of about 13,000 astronomical units, takes roughly 500,000 years to complete one orbit around the binary. This configuration is gravitationally bound, but loosely so. The binding energy is relatively small, and perturbations from passing stars in the galactic neighborhood could, over hundreds of millions of years, potentially disrupt the system. This raises a fundamental question that astronomers have debated for decades. Did Proxima Centauri form together with Alpha Centauri A and B from the same molecular cloud, making them true sibling stars? Or did Proxima form elsewhere and later become gravitationally captured by the Alpha Centauri binary? The question matters because it constrains the formation environment for Proxima's planets and the dynamical history of the entire system. Several lines of evidence bear on this question. Proxima's metallicity is similar to Alpha Centauri A and B, suggesting a common origin. The star's space velocities, their motion through the galaxy, are consistent with gravitational binding rather than a chance alignment. However, chemical abundance patterns show subtle differences that could indicate separate formation sites. Age estimates for the three stars overlap within uncertainties but are not identical, allowing for either shared or distinct origins. Recent simulations of star cluster evolution have shown that capture scenarios are plausible but require specific conditions. Young stars form in clusters containing hundreds or thousands of members. As these clusters disperse over tens of millions of years, close encounters between stars can lead to exchange interactions where one star in a binary is replaced by an interloper. If Alpha Centauri A and B formed in a dense cluster and Proxima passed nearby at low relative velocity, capture could have occurred. Alternatively, all three stars could have formed in the same cluster and remained loosely bound as the cluster dissolved. The implications for Proxima b depend on the timing of planet formation relative to any capture event. If Proxima was captured after its planets formed, the capture process might have dynamically excited planetary orbits, leading to increased eccentricities or altered inclinations. If the capture occurred before planet formation, the planets would have formed under the gravitational influence of the nearby Alpha Centauri binary, potentially affecting the protoplanetary disk's structure and evolution. But there's yet another layer to consider, one that emerges from observations of the Alpha Centauri system's environment and its interactions with the local interstellar medium. The Sun and nearby stars move through a region of space called the local interstellar cloud, a diffuse cloud of gas with densities around a few tenths of hydrogen atoms per cubic centimeter. This cloud is part of a larger structure called the local bubble, a region of low-density, hot gas created by ancient supernova explosions that cleared out denser material. The Alpha Centauri system, located just over 4 light-years away, moves through similar interstellar conditions, but with slight variations in density and composition. Interactions between stellar systems and the interstellar medium can affect planetary environments in subtle ways. Energetic particles from cosmic rays, produced by supernovae and other high-energy events, permeate the galaxy. These particles strike planetary atmospheres, driving additional ionization and chemical reactions beyond what stellar radiation alone produces. The flux of cosmic rays varies depending on the local magnetic field environment and the density of nearby interstellar material. Changes in cosmic ray flux over millions of years could modulate atmospheric chemistry and climate on planets like Proxima b. Additionally, the Sun's heliosphere, the bubble of solar wind that surrounds the solar system, shields the inner planets from some interstellar material and cosmic rays. Proxima Centauri presumably creates a similar astrosphere around its planetary system. The size and shape of this astrosphere depend on the stellar wind's properties and the pressure of the surrounding interstellar medium. A weak stellar wind, or a dense interstellar environment, would result in a smaller astrosphere, providing less shielding for planets. Proxima's stellar wind remains poorly characterized making it difficult to assess how effectively the astrosphere shields Proxima b. These considerations might seem like minor corrections to the main story, but they illustrate the multitude of factors that influence planetary habitability. Every physical process, from the microphysics of atmospheric photochemistry to the galactic scale distribution of supernovae, contributes in some way to shaping the environment of worlds like Proxima b. Yet despite this complexity, patterns emerge. Researchers studying large samples of exoplanets have identified correlations and trends that point toward underlying principles. The radius gap, a dearth of planets with radii between 1.5 and 2 Earth radii, suggests that atmospheric loss processes create a bimodal distribution separating rocky super-Earths from gaseous mini-Neptunes. The valley in the distribution likely results from photoevaporation stripping atmospheres from intermediate-sized planets, leaving behind either bare rocky cores or planets massive enough to retain their gas envelopes. Proxima b, with its estimated radius below 1.3 Earth radii, would place it firmly in the rocky planet population. If it ever possessed a substantial hydrogen envelope during formation, that envelope was lost early, either from photoevaporation or from core-powered mass loss, as residual heat from accretion drove atmospheric escape. The planet we observe today is the remnant, the core and mantle that survived the early epochs of atmospheric stripping. This narrative of atmospheric loss and planetary evolution applies broadly across exoplanet populations. It explains the prevalence of bare rocky cores in close orbits around stars of all types. It accounts for the diversity of planetary densities and the relationships between planet mass, radius, and stellar insolation. And it provides a framework for understanding why potentially habitable zone planets might struggle to maintain atmospheres if they formed too small or orbited too active stars. And yet, the story refuses to close. For every mechanism that strips atmospheres, there are potential mechanisms that replenish them. Volcanic outgassing, comet impacts, erosion of surface minerals by stellar wind, even photochemical production of new molecules from incoming radiation, all represent sources of atmospheric material. Whether replenishment can balance loss depends on the rates of these processes and the timescales over which they operate. For Proxima b, we simply don't know which processes dominate. The question comes down to observations that have not yet been made. Until we directly characterize Proxima b's atmospheric state, we're extrapolating from models, theoretical predictions, and comparisons to other systems. The extrapolations might be roughly correct, or they might miss crucial details that observational data would reveal. This tension between theory and observation drives scientific progress, generating hypotheses that future observations can test. As we look toward those future observations, the technology roadmap becomes critical. What capabilities do we need to definitively answer questions about Proxima b's habitability? Direct imaging stands as the most straightforward approach. If we can photograph Proxima b, separating its faint light from the overwhelming glare of Proxima Centauri, we can measure its brightness in multiple wavelengths, track changes over time as the planet rotates, and potentially detect spectral features from reflected starlight or thermal emission. Current direct imaging techniques struggle with planets as close to their stars as Proxima b, but next-generation coronagraphs and star shades could overcome these challenges. The European Southern Observatory's extremely large telescope, with its 39-meter diameter primary mirror, will carry instruments specifically designed for exoplanet characterization. The METIS instrument, operating at mid-infrared wavelengths, could detect thermal emission from Proxima b if the planet has a warm surface. The Ristretto instrument, designed for high-contrast imaging in visible and near-infrared wavelengths, might resolve Proxima b as a separate point of light, allowing photometric monitoring and rough spectroscopy. These observations won't happen immediately. The ELT is scheduled for first light in the late 2020s. An early observing time will be heavily subscribed by numerous high-priority targets. Proxima b will compete with other nearby potentially habitable planets, with interesting solar system objects, with distant galaxies and quasars, all demanding telescope time. But eventually, over years of accumulated observations, a picture of Proxima b will emerge from the data. Space-based missions offer complementary capabilities. The proposed Large Ultraviolet Optical Infrared Surveyor, LUVOIR, would carry a segmented mirror comparable in size to the James Webb Space Telescope, but optimized for visible and ultraviolet wavelengths, where rocky planets reflect more light relative to their thermal emission. Combined with an internal or external star shade to block starlight, LUVOIR could directly image dozens of potentially habitable exoplanets, including Proxima b, and analyze their atmospheric spectra for signs of oxygen, water vapor, methane, and other biosignature gases. But LUVOIR remains on the drawing board, a concept mission undergoing study by NASA. Whether it will be built and when depends on funding decisions, technology development, and prioritization against other proposed missions. The path from concept to operational telescope spans decades for flagship-class space observatories. If approved, LUVOIR might launch in the late 2030s or 2040s. Closer on the horizon, the Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will carry a coronagraph demonstrator instrument capable of imaging gas giant exoplanets, but not small rocky worlds like Proxima b. However, Roman's observations will advance direct imaging technology and validate techniques that future missions will employ. Each step forward in capability brings us closer to the definitive characterization of nearby potentially habitable planets. Beyond telescopes, interstellar probe missions represent another approach, far more challenging technologically, but offering the ultimate prize of in situ measurements. The Breakthrough Starshot initiative envisions tiny probes accelerated to 20% of light speed using powerful ground-based lasers. At such velocities, a probe could reach Alpha Centauri in about 20 years after launch. The probes would carry miniaturized cameras and sensors, transmitting data back to Earth during a brief flyby of the system. The technical challenges are immense. Accelerating even a gram-scale probe to relativistic velocities requires gigawatt-scale laser arrays with extraordinary beam coherence and pointing accuracy. The probes must survive acceleration forces, interstellar dust impacts, and the harsh radiation environment of space. Communications across 4 light-years, using only milliwatts of transmitter power, pushes the limits of receiver sensitivity. Yet preliminary studies suggest these challenges, while formidable, are not physically impossible. If sufficient resources and engineering ingenuity are applied, an interstellar flyby mission could be achieved within this century. For Proxima b, an interstellar probe would provide images at resolutions comparable to what we have for Mars or Venus from spacecraft. It could measure atmospheric composition directly, detect magnetic fields, map surface features, and search for signs of geological activity. A single flyby, lasting just hours as the probe zips through the system at 60,000 kilometers per second, would revolutionize our understanding more than centuries of telescopic observations could achieve. But we need not wait for such missions to make progress. The next decade of observations with JWST, ground-based, extremely large telescopes, and other facilities will constrain many open questions even without direct imaging or interstellar probes. Each observational campaign, each new spectrum, each detection or non-detection of atmospheric features adds pieces to the puzzle. And this is where the narrative opens into its deepest implications. The questions that extend far beyond Proxima b itself into the nature of planets, stars, and life in the universe. What Proxima b represents, ultimately, is a test case for our models of planetary habitability. It occupies a position that should be habitable according to classical definitions. Yet every detailed examination reveals challenges that complicate that simple assessment. This tension between theoretical habitability and observed reality forces us to refine our understanding, to recognize that the habitable zone is a necessary but insufficient condition for life. Location matters, but so do stellar activity, atmospheric retention, magnetic fields, geological processes, and dozens of other factors that interact in complex ways. The lessons learned from Proxima b will inform how we interpret thousands of other planets discovered around M-dwarfs. When TESS or future missions identify new potentially habitable worlds around red dwarfs, the assessment of their true habitability will depend on what we've learned here. Are they orbiting particularly active stars? Do they show signs of atmospheric loss? What are the implications of their orbital architectures? The framework we build from studying Proxima b becomes the template for evaluating all similar systems. This is why the stakes are so high, why so much effort and telescope time is directed toward this one planet. Proxima b is not special because it is unique. It is special because it is typical of the most common type of potentially habitable planet in the galaxy, yet close enough to study in detail. Every answer we obtain, every parameter we constrain, every mechanism we identify as important or negligible scales up to affect our understanding of billions of worlds. Yet there is something else emerging from recent research, something that suggests the story is about to shift in an unexpected direction. The comparative studies of M-dwarf systems have revealed patterns, but also anomalies. Some planets retain atmospheres where models predict loss. Others lose atmospheres under conditions that should allow retention. The scatter in outcomes is larger than theoretical uncertainties can explain. This suggests missing physics, processes we haven't properly modeled, or factors we haven't recognized as important. One possibility that has gained traction involves the timing and nature of planet formation relative to stellar evolution. If planets form before the star reaches the main sequence, they endure the intense pre-main sequence activity phase. But if planet formation is delayed, perhaps by dynamical disruptions in the protoplanetary disk or slow accretion processes, planets might arrive at their final configurations after the star has already settled into a calmer state. The same planet at the same orbital distance would experience dramatically different conditions depending on when it formed. Another factor involves the three-dimensional structure of stellar magnetic fields and how they channel stellar wind. Recent Magneto-hydrodynamic simulations of M-dwarf magnetospheres show that the magnetic field topology can create regions of enhanced or reduced wind density. Planets orbiting within protected regions, essentially in the magnetic shadow of stellar field structures, might experience lower particle bombardment than those exposed to the full stellar wind. These magnetic geometries change over time as the stellar dynamo evolves, meaning planetary exposure to harsh conditions might vary over millions of years. These subtleties illustrate why predicting planetary outcomes from stellar properties alone proves so difficult. The devil truly lives in details, in the specific history of each system and the particular configuration of magnetic fields, orbital dynamics, and planetary properties that combine to create a unique environment. And yet, despite the complexity, the search for patterns continues, because beneath the noise of individual variations, universal principles must operate. Physics and chemistry work the same throughout the universe. The laws governing stellar evolution, atmospheric dynamics, and geological processes apply equally to Proxima b and to planets thousands of light years distant. Our task is to separate the universal from the contingent, to identify which factors always matter and which depend on local circumstances. This synthesis of observation and theory, this iterative refinement of models against data, defines the scientific enterprise. We propose mechanisms, predict outcomes, compare predictions to observations, and revise our understanding when discrepancies emerge. The process is messy, nonlinear, and sometimes frustratingly slow. But over time, clarity emerges. Patterns become visible. Understanding deepens. For Proxima b, we stand at an intermediate stage in this process. We know enough to recognize that simple optimism about habitability was unwarranted. The challenges are real, the environment harsh, the prospects for life uncertain at best. But we don't know enough to rule out all possibilities. The planet might surprise us. Nature often does. The universe contains more variety, more unexpected solutions to physical problems than our limited imaginations can anticipate. As we prepare to move into the final part of this exploration, the focus will shift from what we know about Proxima b to what that knowledge means for the broader questions of habitability and life in the universe. The specific details of one planet's environment matter primarily because they illuminate principles that apply universally. And those principles, still being discovered, still being refined through observation and theory, point toward insights that reach far beyond our nearest stellar neighbor, into the deepest questions about our place in the cosmos. The instruments are being built. The observations are being planned. The theoretical frameworks are being developed. Within the next decade or two, many of the uncertainties surrounding Proxima b will resolve into concrete knowledge. We will know whether it has an atmosphere, what the atmosphere contains, whether geological activity persists, whether the surface could support liquid water. These answers will reshape how we think about planets around red dwarfs and about the prevalence of habitable conditions in the galaxy. But even as those specific questions find answers, new questions will emerge. They always do. Each resolved mystery reveals deeper puzzles. Each answered question spawns follow-ups. The frontier of knowledge advances, but never reaches a final destination. And in that endless progression lies both the frustration and the beauty of scientific inquiry. What began as excitement about a nearby potentially habitable planet has evolved into a profound examination of stellar activity, atmospheric physics, planetary dynamics, and the complex interplay of factors that determine whether a world can support life. The journey from simple hope to nuanced understanding reflects the maturation of exoplanet science from its infancy in the 1990s to its current sophisticated state. We have learned to ask better questions, to recognize complexity where we once saw simplicity, to appreciate the challenges while maintaining the curiosity that drives exploration forward. Proxima b stands as a monument to that evolution, a world that refuses easy categorization, that challenges our assumptions, that demands careful study and rewards, that study with insights applicable far beyond its own small sphere of rock and potential atmosphere, orbiting a dim red star in the cosmic next door. What we've discovered so far represents merely the opening chapters of a longer story, a story that continues, that deepens, that reaches toward truths we have not yet imagined. And the most remarkable aspect of this entire investigation is that it concerns a place we might one day actually visit. Not in our lifetimes, almost certainly, but within the span of human civilization, possibly within centuries. Technology might advance sufficiently to send robotic explorers, perhaps even human expeditions, to the Alpha Centauri system. When that day comes, when sensors descend through Proxima b's atmosphere, if it exists, when instruments touch its surface and analyze its rocks and search for any whisper of biological processes, the questions we've explored here will finally receive definitive answers. Until then, we continue the work, observing, modeling, analyzing, synthesizing, building the knowledge base that will guide future missions and shape humanity's expansion into the cosmos. Because Proxima b, regardless of whether it harbors life, regardless of whether humans ever set foot there, represents something profound. It is a world at the edge of our reach, a place where imagination meets physics, where hope encounters reality, and where the universe reveals, slowly and grudgingly, the secrets of how planets, stars, and possibly life emerge from the laws that govern all of existence. The universe does not arrange itself for human convenience. This simple truth underlies everything we have learned about Proxima b and the broader population of planets orbiting red dwarf stars. We sought habitable worlds in the easiest places to look, around the most common stars, at distances close enough for detailed study. What we found instead was complexity, challenge, and a humbling reminder that nature's solutions rarely match our expectations. Yet within that complexity lies information, patterns waiting to be decoded, principles waiting to be understood. The story of Proxima b is ultimately a story about how science confronts the unexpected and transforms confusion into clarity. Let us now consider what all of this means for the search for life beyond Earth and for humanity's future among the stars. The habitable zone concept, that elegant calculation of stellar flux and planetary temperature, served exoplanet science well during its early decades. It provided a framework for prioritizing observations, a way to sort the growing catalog of discovered worlds into those worth studying further and those that could be set aside. But as our knowledge deepened, the framework's limitations became apparent. The habitable zone is a necessary condition, not a sufficient one. A planet within the zone might be habitable, or it might be a scorched rock, a frozen ice ball, or something else entirely that defies simple categorization. Proxima b occupies the habitable zone, So do TRAPPIST-1e, F, and G. So do dozens of other planets around M dwarfs detected by Kepler, TSES, and ground-based surveys. Yet for each of these worlds, detailed examination reveals complications that simple habitability calculations do not capture. Stellar activity strips atmospheres. Tidal locking creates extreme climate contrasts. Photochemistry destroys potential biosignatures. The zone defines where liquid water could exist on an idealized planet around an idealized star. Real planets and real stars rarely match those ideals. This recognition has driven a shift in how astrobiologists think about habitability. The emerging framework emphasizes planetary systems rather than individual planets, stellar evolution rather than static properties, and the dynamic interplay of processes rather than equilibrium states. A planet's habitability depends not just on its current position, but on its entire history, from formation through billions of years of evolution. The factors that matter extend far beyond simple temperature calculations into realms of atmospheric chemistry, geological activity, magnetic field dynamics, and stellar behavior that change over time. For M-dwarf systems, this expanded framework paints a challenging picture. The very properties that make red dwarfs appealing targets for exoplanet searches, their abundance, their longevity, their small sizes that make planet detection easier, also create hostile conditions for planetary habitability. The pattern is not absolute. Exceptions might exist, planets that through some combination of favorable circumstances maintain habitable conditions despite the general trends. But the statistical likelihood of finding such exceptions appears lower than early optimism suggested. And this is where the data forces uncomfortable conclusions. If M-dwarf planets struggle to maintain habitable conditions, then the galaxy's habitable real estate might be concentrated around less common stellar types. Sun-like G-dwarfs and slightly cooler K-dwarfs, together comprising perhaps 15% of all stars, might host the majority of truly habitable worlds. The remaining 85%, dominated by M-dwarfs, might offer abundant rocky planets, but few genuine candidates for life. This conclusion, if correct, has profound implications for the search for extraterrestrial intelligence and for estimates of how common life might be in the universe. The Drake equation, that famous framework for estimating the number of communicative civilizations in the galaxy, includes a factor for the fraction of planets that develop life. If most planets around most stars face insurmountable habitability challenges, that fraction shrinks correspondingly. The galaxy might be filled with planets, yet largely empty of life. However, the conclusion rests on assumptions that remain untested. We have characterized atmospheres for only a handful of M-dwarf planets. The sample is small, biased toward easy targets, and potentially unrepresentative of the broader population. Every negative result for atmospheric detection could be balanced by positive detections on planets not yet observed. The systematic surveys needed to draw firm statistical conclusions are only beginning. Moreover, life's resilience and adaptability might exceed our expectations. Extremophiles on Earth occupy niches we once thought completely sterile. If life can adapt to boiling temperatures, crushing pressures, extreme acidity, and intense radiation on our own planet, perhaps it can adapt to conditions we consider hostile on exoplanets as well. The assumption that Earth-like conditions are necessary for life is just that, an assumption, until we find life elsewhere. or definitively rule it out in specific environments. We cannot know how constraining those conditions truly are. But here's where the story bends in an unexpected direction. The challenges facing M-dwarf planets might paradoxically make them more interesting from certain perspectives. Adversity drives evolution. Harsh conditions force adaptation. If life ever arose on a world like Proxima b, it would have done so under extreme selective pressures that might produce forms radically different from terrestrial life. Consider the implications of tidal locking. A world with one hemisphere in perpetual daylight and another in eternal darkness offers distinct ecological niches separated by a twilight zone. Life might specialize for these different environments, developing along entirely separate evolutionary trajectories on a single planet. The day side might host photosynthetic organisms adapted to continuous intense radiation. The night side might harbor chemotrophs, drawing energy from geological processes. The terminator zone might see the most complex ecosystems, where resources from both sides converge. Alternatively, if life exists only in protected subsurface environments, cut off from stellar radiation, it might develop along lines completely unlike surface-dwelling terrestrial organisms. Without photosynthesis as a primary energy source, such life would depend entirely on chemical gradients, geothermal heat, or other non-solar energy. The ecosystems might be sparse by Earth standards, but they could be ancient and stable, persisting for billions of years in conditions that change only slowly. These speculations illustrate how thinking about Proxima b expands our conception of what alien life might look like. We cannot assume that extraterrestrial organisms will resemble terrestrial ones even in basic biochemistry. Carbon-based life using water as a solvent remains the most plausible hypothesis, given the chemistry of the universe. But the specific forms that life takes depend on environmental conditions that vary enormously across different planets. And yet, speculation about alien life must be balanced with scientific caution. We have exactly one example of life in the universe, the biosphere of Earth. Drawing general conclusions from a sample of one is statistically fraught. Every statement about what life needs or can tolerate is really a statement about terrestrial life, which might or might not generalize. Until we find a second example, whether on Mars in the subsurface oceans of Europa, or Enceladus, or on an exoplanet like Proxima b, we cannot know how universal or parochial terrestrial biology truly is. This epistemic limitation drives much of the urgency in astrobiology. Finding life elsewhere, anywhere, would instantly transform our understanding. Even a single microbe on Mars or in the ice of Europa would tell us that life arises readily given appropriate conditions, that the universe tends toward biology when chemistry permits. Conversely, continued failure to find life despite extensive searching would suggest that life's origin is rare, that we might be alone or nearly so in the cosmos. Proxima b occupies a peculiar position in this search. It is close enough that, in principle, we might someday visit it. Robotic probes, if Breakthrough Starshot or similar initiatives succeed, could reach the Alpha Centauri system within decades of launch. But even the most optimistic scenarios place such missions far in the future. For the foreseeable future, Proxima b will be studied remotely, through telescopes and models, not through direct exploration. Yet remote study can still provide meaningful constraints on the question of life. If future observations reveal an oxygen-rich atmosphere on Proxima b, That would constitute a potential biosignature, since free oxygen in substantial quantities typically requires continuous production by photosynthetic organisms. If we detect methane alongside oxygen, the disequilibrium would strengthen the case further. Atmospheric chemistry offers windows into surface processes that might, with careful interpretation, reveal the presence of biology. The challenge lies in avoiding false positives. Non-biological processes can produce oxygen and methane under certain conditions. Photolysis of water vapor, followed by hydrogen escape to space, can leave behind accumulated oxygen on a lifeless planet. Volcanic outgassing or serpentinization reactions can produce methane without any biological involvement. Distinguishing biological from abiotic sources requires detailed spectroscopy, contextual knowledge about the planet's geology and atmospheric dynamics, and careful consideration of alternative explanations. This is where the scientific enterprise becomes painstaking and slow. Each potential biosignature must be evaluated against multiple hypotheses. Each observation must be replicated and confirmed. The burden of proof for claiming the detection of extraterrestrial life is extraordinary, as it should be. Premature announcements of discovery, later retracted or questioned, damage scientific credibility and public trust. The history of astrobiology contains several such episodes, from the Martian meteorite ALH 4001 controversy in the 1990s to disputed detections of phosphine in Venus's atmosphere in 2020. Each case illustrates the difficulty of making extraordinary claims stick. For Proxima b, any future detection of potential biosignatures will face intense scrutiny. The scientific community will demand rigorous analysis, exploration of alternative explanations, and confirmation from independent observations. This process might take years or decades. Patience is required, both from scientists and from the public. But the patience is worthwhile. If we eventually conclude with high confidence that life exists on Proxima b, that conclusion will rest on foundations strong enough to withstand any challenge. And this brings us to a deeper reflection on what the search for life represents in human terms. The question of whether we are alone in the universe is among the oldest and most profound that humans have asked. Ancient philosophers speculated about other worlds and other beings. Religious traditions offered their own answers, some affirming cosmic uniqueness, others populating the heavens with diverse creatures. Modern science has transformed the question from speculation into empirical investigation, but the underlying wonder remains the same. Finding life beyond Earth would not just be a scientific discovery, it would be a cultural milestone, a reshaping of humanity's self-understanding. For centuries, we have operated under the assumption, implicit or explicit, that Earth is special, that our existence represents something unique in the cosmos. Discovering that life arises elsewhere would dissolve that assumption, placing us in a universe that produces life routinely, a universe where our existence is normal rather than exceptional. The psychological and philosophical implications are difficult to predict. Some might find comfort in the knowledge that we are part of a larger living cosmos. Others might experience a diminished sense of significance, a humbling recognition that humanity is one among countless instances of life in an infinite universe. Religious and philosophical frameworks would need to adapt, as they have adapted to previous revolutions in scientific understanding, from the heliocentric solar system to evolutionary biology. But we are getting ahead of ourselves. We have not yet found life on Proxima b or anywhere else beyond Earth. The question remains open, and the search continues. What we can do now is pursue that search rigorously, accumulating evidence, refining models, and preparing for whatever answers eventually emerge. Let us return to the specific science of Proxima b and consider what the next decade of observations might reveal. The James Webb Space Telescope, despite not being optimized for studying non-transiting planets like Proxima b, has already contributed to our understanding of the system. Observations of Proxima Centauri's infrared emission provide data on stellar activity at wavelengths inaccessible from the ground. Studies of other M-dwarf systems offer comparative context. As JWST's operational lifetime extends, additional observing programs targeting Alpha Centauri and its planets will likely be approved. Ground-based, extremely large telescopes represent the most promising near-term capability for characterizing Proxima b. The European Extremely Large Telescope's METUS instrument, operating at mid-infrared wavelengths between 3 and 13 micrometers, could detect thermal emission from Proxima b if the planet has a sufficiently warm surface. The observation would require hundreds of hours of integration time, carefully scheduled to catch the planet at maximum separation from the star, but it lies within the telescope's projected capabilities. The Ristretto project, specifically designed for high-resolution spectroscopy of Proxima b's reflected light, aims to measure the planet's atmospheric composition by detecting absorption features imprinted on starlight, reflected from the planet's surface and atmosphere. This approach works best if the planet has a substantial atmosphere with distinctive spectral features, such as water vapor, carbon dioxide, or molecular oxygen. If Proxima b is airless or has only a tenuous atmosphere, Ristretto might detect only the bare surface, revealing composition through reflectance properties rather than atmospheric absorption. The 30-meter class telescopes under construction will also advance direct imaging capabilities for nearby planetary systems. Coronagraphic instruments designed to suppress starlight while preserving planet light will achieve contrasts of 1 part in 10 million or better, sufficient to detect young Jupiter-like planets in nearby star systems. Whether these instruments can reach the contrasts needed for Earth-sized planets in habitable zones remains uncertain, but technology development continues apace. Space-based coronagraph missions, though currently in early study phases, offer the ultimate capability for characterizing potentially habitable planets around nearby stars. The Habitable Worlds Observatory, a concept under consideration by NASA following the Astro 2020 Decadal Survey recommendations, would carry a large segmented mirror and advanced coronagraph or starshade system optimized for detecting Earth-like planets in reflected light. Such a mission, if approved and built, might launch in the late 2030s or 2040s and would be capable of detecting and characterizing dozens of potentially habitable exoplanets, including Proxima b, if observation geometry permits. Interferometric techniques offer another path forward. Arrays of telescopes operating in concert can achieve angular resolution far exceeding what any single telescope can provide. The Very Large Telescope Interferometer in Chile already demonstrates this principle, combining light from multiple 8-meter telescopes to resolve details at millisecond scales. Future space-based interferometers, though technically challenging, could achieve micro-arcsecond resolution sufficient to map the surfaces of nearby exoplanets and detect biosignatures in their atmospheric spectra. These technological possibilities illustrate that the questions surrounding Proxima b are not permanently unanswerable. They are temporarily unanswered, awaiting instruments and observations that are already being planned and built. The timeline stretches across decades, requiring patience that spans human generations, but progress is being made. However, the deeper researchers have looked into the Proxima system, the more they have realized that planetary characterization alone might not resolve the habitability question. The system's history, stretching back billions of years, contains events and processes that shaped current conditions in ways that direct observation cannot recover. Consider the question of water delivery. Rocky planets in the inner regions of planetary systems typically form dry, accreting mainly silicate and metallite materials with limited volatile content. Water and other volatiles arrive later, delivered by asteroids and comets from the outer system where ices condense. The amount of water a planet receives depends on the architecture of the system, the population of volatile-rich bodies available for delivery, and the timing and intensity of bombardment episodes. For Proxima b, we know nothing directly about the system's early bombardment history. If an asteroid belt or Kuiper belt analog exists in the Proxima system, it has not been detected. The presence of Proxima c, if confirmed, suggests material existed at larger orbital distances during formation, but the fate of smaller bodies, planetesimals, and comets remains unknown. Whether Proxima b received a substantial volatile delivery, allowing it to develop oceans and an atmosphere, or remain dry throughout its history, cannot be determined from current data. Similarly, the geological history of Proxima b influences its present state, but cannot be directly observed. Did the planet experience global magma ocean phases that outgassed a thick atmosphere? Did plate tectonics ever operate, recycling volatiles and regulating climate through carbon silicate cycling? Is there any geological activity today, or has the interior cooled to quiescence? These questions require either direct exploration or indirect inferences from atmospheric and surface observations that remain beyond current capabilities. The limitations highlight a fundamental challenge in exoplanet science. We observe snapshots, moments in planetary evolution that represent current conditions, but reveal little about past states. Reconstructing history requires models that make assumptions about initial conditions and evolutionary processes. Assumptions that might or might not reflect reality. For well-studied planets like Mars and Venus, spacecraft exploration has provided constraints that allow historical reconstruction with some confidence. For exoplanets, we lack that direct access. Yet even within these limitations, progress continues. Statistical analyses of exoplanet populations reveal trends that inform individual planet characterization. Laboratory experiments simulate atmospheric chemistry and surface processes under extreme conditions. Numerical models grow more sophisticated, incorporating more realistic physics and exploring wider parameter spaces. Each advance provides new tools for interpreting observations and reducing uncertainties. And this brings us to perhaps the most profound question raised by the study of Proxima b and M-dwarf planets generally. Not whether life exists on these worlds, but whether habitable planets are common or rare in the universe. The Copernican principle, the philosophical stance that Earth occupies no special position in the cosmos, has guided scientific thinking for centuries. Extended to biology, It suggests that life should arise wherever conditions permit, that Earth is typical of habitable planets, and that the universe should teem with life. This optimistic perspective has motivated much of the search for extraterrestrial intelligence and underlies popular assumptions about the prevalence of alien civilizations. But the evidence from dwarf studies challenges easy optimism. If the most common stars in the galaxy struggle to maintain habitable conditions on their planets, then habitable environments might be rarer than Copernican reasoning suggests. Earth might not be typical. The conditions that allowed life to arise and flourish here might represent a fortunate convergence of circumstances that occurs only occasionally. This possibility, sometimes called the rare Earth hypothesis, suggests that while simple microbial life might be relatively common, complex life and intelligence might be rare or unique. The factors required for complexity, stable climate over billions of years, protection from sterilizing radiation, sufficient planetary mass and geological activity, might align infrequently. Earth might represent not a typical outcome, but an exceptional one, a planet where everything happened to go right. The truth almost certainly lies somewhere between the extremes of a universe teeming with life and a cosmos where Earth stands alone. The question is where on that spectrum reality falls, and answering it requires far more data than we currently possess. Proxima b contributes to this larger puzzle. If we eventually determine that the planet is sterile, stripped of atmosphere, and baked by stellar radiation, it becomes one more data point, suggesting that dwarf planets struggle with habitability. If we discover signs of life, it demonstrates that biology can persist under conditions far harsher than Earth's, expanding our sense of where to search. Either outcome advances understanding, but there's another way to frame the question. One that focuses not on the prevalence of life, but on the nature of habitability itself. What does it mean for a planet to be habitable? The traditional definition emphasizes surface liquid water and Earth-like conditions. But this definition reflects our biases more than cosmic reality. Habitability might be better conceived as a spectrum rather than a binary category. Planets range from completely sterile to fully habitable, with most occupying intermediate states. A planet with subsurface oceans but a frozen surface is partially habitable. A world with a thick, toxic atmosphere but potentially habitable high-altitude zones is partially habitable. Even a planet with surface liquid water but intense radiation might support some forms of life while excluding others. Under this expanded conception, Proxima b's status becomes less about whether it meets arbitrary thresholds and more about understanding where it falls on the habitability spectrum. It might not be Earth-like, but it might still be interesting biologically. The forms of life it could support, if any, might differ radically from terrestrial organisms while still qualifying as alive by any reasonable definition. This perspective also suggests different search strategies. Rather than focusing exclusively on planets that match Earth's conditions, we might broaden our search to include worlds with partial or alternative habitability. The signatures we seek might differ from classic biosignatures like oxygen and methane, requiring new approaches and new instruments optimized for different atmospheric compositions. And yet, practical constraints limit how broadly we can search. Telescope time is finite. Funding is limited. Priorities must be set. The strategy of focusing on the most Earth-like candidates makes sense given resource constraints, even if it risks missing exotic life forms in unexpected environments. As capabilities expand, the search can broaden correspondingly. For the coming decade, Proxima b will remain a prime target precisely because it is close, because it orbits in the habitable zone, however imperfectly that concept applies, and because it offers the best opportunity to test our models of dwarf planetary habitability. What we learn will inform observations of more distant systems, shaping target selection and interpretation for generations of future surveys. Let us now consider the longer-term future, the possibilities that extend beyond current technological horizons into speculative but physically plausible territory. The Breakthrough Starshot initiative, mentioned earlier, represents humanity's most serious attempt to plan an interstellar mission. The concept involves thousands of tiny spacecraft, each weighing about a gram and carrying miniaturized cameras, sensors, and communication equipment. These craft would be accelerated to roughly 20% of light speed using enormous ground-based laser arrays that push against reflective light sails attached to each probe. At such velocities, the journey to Alpha Centauri would take approximately 20 years. The technical challenges are immense but not insurmountable. The laser array would need to deliver gigawatts of power with extraordinary precision, tracking the tiny sail as it accelerates and keeping the beam focused over thousands of kilometers. The probes must survive acceleration forces equivalent to tens of thousands of Earth gravities, though the acceleration occurs over minutes rather than instantaneously. In transit, the probes must endure impacts from interstellar dust at relativistic velocities, requiring either shielding or redundancy across thousands of individual craft. Upon arrival at Alpha Centauri, the probes would have only hours to observe the system before speeding past into interstellar space. Communication back to Earth would be extraordinarily challenging, requiring sensitive receivers to detect the faint signals from milliwatt transmitters across 4 light-years. But the potential scientific return would be revolutionary. Direct images of Proxima b at resolutions comparable to spacecraft observations of Mars would answer many of the questions that remain open today. Breakthrough Starshot remains in the research and development phase. The laser technology, light sail materials, and miniaturized sensors all require advances beyond current capabilities. Optimistic timelines suggest a possible launch in the 2040s or 2050s, with arrival at Alpha Centauri in the 2060s or 2070s. More conservative estimates push these dates further into the future. But the project represents a serious engineering effort, backed by substantial private funding, not mere science fiction speculation. Beyond Starshot, other interstellar mission concepts have been proposed over the decades. Nuclear pulse propulsion, using detonation of nuclear devices to push a spacecraft, could achieve velocities of a few percent of light speed, enabling journeys to nearby stars in centuries rather than millennia. Fusion rockets, if ever developed, might achieve similar performance. Even more speculative concepts, from antimatter engines to warp drives, appear in theoretical literature, though they require physics beyond current technology, or possibly beyond current physical law. The dream of interstellar travel has captured human imagination for generations. Proxima b, as the closest potentially habitable exoplanet, crystallizes that dream into a specific destination. Whether humans will ever walk on its surface, or even send robots to study it directly, depends on technological and societal developments impossible to predict. But the possibility motivates research, inspires innovation, and reminds us that the universe extends far beyond our immediate neighborhood. And this is where the story reaches toward its conclusion. Not an ending, but a transition into ongoing inquiry. What have we learned from this deep examination of Proxima b and the broader context of M-dwarf planetary systems? We have learned that the habitable zone is a starting point, not a destination. A planet within the zone might be habitable or might face challenges that render it sterile. The zone identifies candidates for further study, but study reveals complexity that simple calculations cannot capture. We have learned that stellar activity matters profoundly for planetary habitability. M-dwarf stars, though long-lived and abundant, produce radiation environments that challenge atmospheric retention and surface habitability. The flares, stellar winds, and magnetic storms that characterize these stars create conditions far harsher than planets around sun-like stars experience. We have learned that planetary systems are dynamic, evolving entities. The architecture we observe today results from billions of years of orbital evolution, tidal interactions, and possibly capture or exchange events. Understanding current conditions requires reconstructing historical processes that leave only indirect traces. We have learned that our models, while sophisticated, remain incomplete. Discrepancies between predictions and observations reveal missing physics, processes not yet incorporated, and factors not yet recognized. The scientific enterprise proceeds by identifying and resolving such discrepancies, iteratively improving understanding. We have learned that the search for life requires patience and rigor. Extraordinary claims demand extraordinary evidence. The protocols for detecting biosignatures and ruling out false positives are stringent because the stakes are high. A premature or incorrect announcement would damage scientific credibility far more than a delayed but correct one. And we have learned that Proxima b, for all its challenges, remains a world worth studying. It is close. It is accessible to current and near-future instruments. It raises questions that illuminate broader issues in planetary science and astrobiology. Whether or not it harbors life, understanding it advances our comprehension of planets, stars, and the conditions that might allow biology to emerge and persist. The dark truth about our nearest neighbor was never just about one planet's hostile environment. It was always about what that hostility reveals, about the systematic challenges facing planets around the galaxy's most common stars, about the complex interplay of factors that determine habitability, about the humbling recognition that the universe is under no obligation to provide convenient homes for life. Yet within that recognition lies something else, not despair, but determination, not resignation, but resolve. The universe may be indifferent, but we are not. We ask questions. We build instruments. We launch missions. We seek answers. The search for life beyond Earth continues not because success is guaranteed, but because the question matters too much to leave unanswered. Proxima b will be studied for decades, perhaps centuries to come. The questions it raises will eventually find answers, whether through remote observation, robotic exploration, or technologies we cannot yet imagine. And those answers, whatever they turn out to be, will shape humanity's understanding of its place in the cosmos. The story does not end here. It continues in every observation, every model, every theoretical advance, every new instrument pointed toward the stars. What began as a simple announcement in 2016, a planet orbiting our nearest stellar neighbor, has grown into a profound investigation of habitability, stellar physics, planetary evolution, and the conditions for life. That investigation remains incomplete, as all scientific investigations ultimately are. But we have learned much. We have learned that the dark truth about Proxima b was only the beginning. And we have learned that the beginning, however challenging, opens onto paths that lead toward deeper understanding, broader perspective, and perhaps, someday, the answer to the most profound question of all. Are we alone? The search continues. There is a question that has haunted astronomers since the first exoplanet detections in the 1990s. A question that Proxima b forces us to confront with unusual directness. If habitable planets exist around the nearest stars, and if those planets have had billions of years to develop life, and if life tends toward complexity and intelligence over evolutionary time, then where is everyone? This is the end of part 1, to be continued.